Hi. So welcome to this webinar on petroleum thermodynamics, our common equations. This is a really special webinar for us. That's going to be basically presented, and the material is going to be presented by Dr. Curtis Hayes Whitson. I'll introduce the speaker a little bit later, but before that, I thought to just run you through a few meeting logistics. So first of all, we have a lot of registered participants today, and I know there's a special day for a lot of people today, so many is not working. So I know a lot of you will access this after the fact, but at least for those that's in the Teams meeting today, everybody is muted by default, but that does not mean that you can't ask any questions. So if you have any questions, use the Q&A chat box down here to the right. The presentation is supposed to be between 45 to 60 minutes, followed by a Q&A. As mentioned, we are recording. The meeting is facilitated by Whitson, and Whitson is a company that tries to exhibit its love for petroleum engineering, production engineering, PVT, reservoir, etc. through a couple of our software platforms. One of those are Whitson Plus. I know these days everybody wants to get the most bang for their buck, and Whitson Plus is essentially a way for you to get access to all the functionality you see here to the right in one interface. We also love to teach about the topics we talk about in these webinar series. All the courses we're offering you can find on our webpage at whitson.com/training. There you find our software courses, you find our public courses, and you find the next webinars that is coming up. The next webinar is already in May with Vivek from Oxy. It's going to be a super interesting presentation as well. So go into whitson.com/training if you'd like to see more of content like this. The last thing that's worth mentioning is kind of the gentleman's agreement to this webinar series. And I know a lot of you think that it's free to join the webinar today, and it's kind of basically free. The only thing we hope that you can do is to go into our LinkedIn page and click follow. And why is it called a gentleman's agreement? Well, we won't be there on the other side to check if you're doing it or not, but we would really appreciate that if you could. If you are in the US and are interested in everything related to PVT, bottom hole pressures, RTA, flow material balance, numerical modeling, nodal analysis, etc., we're hosting a yearly conference called WITCON in Houston in October. That's the week just before ATCE. So if you're traveling into Houston or to Texas for ATCE in San Antonio the week after, it's a perfect opportunity for you to also join WITCON in October. So just email me if you want more information about that. So with that, I'll introduce the speaker. I'm lucky to know the speaker very well. He is in addition to being a doctor in petroleum engineering, he has his bachelor's degree from Stanford University and finished his PhD at NTNU, where he is also a professor and has been since the 80s. He's also the founder of Whitson, which was earlier called Para, and also Petrostreams that is now a part of the Quorum system. He's also the creator and developer of PVT-X, has written numerous books in the industry, with probably the SBE phase behavior monograph being the most known, but also the well performance book in 1980 or in the 1980s with Mike Golan, and last but not least is a long-term friend and mentor of myself. So with that, Curtis, I'll just go ahead and stop sharing and mute myself.
Okay. Let's see. All right. Can you see the screen now? I guess, yeah. and I guess myself, I'm also sharing the video. So thanks, Matthias, for the introduction, and I want to walk you through this presentation on petroleum thermodynamics, our common equations. It's not just a bunch of equations for a short hour, but there are a few, and behind some of the other slides, there's a lot of equations to actually get to some of the topics that we're talking about. It's actually a presentation that I made a couple of years back at at the invitation of Mohammed Riazi, who some of you may know, has written several books on characterizing petroleum fluid systems. And basically, it was a conference that was trying to bridge the discussion of petroleum thermodynamics for all the way from upstream, where we mainly work reservoir production, surface processing, down to transportation and including refining. So it was kind of an attempt to do that, but mainly from a perspective like I represent, which is for the most part upstream. So we'll get started on this. So the four topics I wanted to just touch on were the development of equations of state that I think we're all a bit familiar with, some more than others. And then how to solve those equation of state models to do phase equilibrium calculations, bubble point, dew point, phase diagrams, critical point, and compositional grading, miscibility calculations, things like that. And then basically how to tune an equation of state model to a specific collection of fluids, like a reservoir. What we're doing in the North American tight unconventional is actually developing equation states that are valid for essentially all the wells in a given basin, like the Eagle Ford or Permian, and so forth. So how do we do that model tuning? Who kind of did the early model tuning in the industry, and how's that done? And then finally, just a couple of simple examples, not really simple examples, but a couple of examples about how we couple the equilibrium calculations with equations of state transport in porous media and pipes and so forth. So these are the topics I want to go through. But when I put this presentation together, I did it with the fact that just prior to the meeting, Michael Mickelson had just passed away, as had Keith Coates and Ken Starling. And these are three men who had an enormous effect on my journey to where I'm at today, and understanding and applying and working with thermodynamics and petroleum systems. And so I just wanted to kind of make a presentation that emphasized some of their contributions, which are pretty comprehensive when it comes to the topic. So anyway, I'll go through a little bit from each of those folks' contributions. So Keith Coates, he did all his degrees at the University of Michigan. He went to work for SO Production Research. And thereafter, he was a short stint as a professor at University of Michigan and then University of Texas before he basically broke out, and the rest of his life was doing independent consultancy. He built companies around the consultancy and the reservoir simulators that he built, many of during his life. And one thing about Keith is that he basically was very open in publishing pretty much everything innovative and new that he was doing. Any new model that became commercial, he was writing a paper or two discussing the details of what was in that reservoir simulation model. So he was from around the late 70s applying computational thermodynamics in equation of state-based compositional reservoir simulators to describe transport and porous media. He wrote some of the earliest compositional and thermal reservoir simulators. I'll go through a couple of those. He also had, I think, the earliest paper on using equation of state, cubic equations of state to develop basically the equation of state specifically to a collection of samples for a given field, and doing the model tuning with regression methods for the Peng-Robinson and Redlich-Kwong equations of state. Way back in the day, he also did a lot of work on underground storage of gases, which is now again becoming very important to our industry, and particularly in using underground storage of both hydrogen and CO2. So he did a lot of work there. If you want to go back to this 50s and 60s when he first started writing papers. But when it comes to the use of the equation of state, that really started in around 1979 when he wrote the so-called Comp1 simulator. It was a fully implicit, the first commercial compositional EOS-based reservoir simulator. He then presented the paper where he wrote a package to develop EOS specific to reservoir fluid systems based on tuning of laboratory PVT data for multiple samples in a given field, including gas injection type studies like dwelling tests and critical transition from oil to bubble point to dew point systems. And that was in '83. Then he came with a fully implicit composition reservoir simulator for both single and dual porosity, so-called Comp4. And this was not too long before he left and went on his own in Coates Engineering. And there he developed his call it Life Legacy Simulator Sensor, which came out in 1998 and was published then and is still being used by many companies in the industry. And that's both a black oil and compositional simulator where the formulation is identical for the two formulations, just how the PVT routines work differently. Ken Starling, he did his bachelor and master's degree at Texas A&I. He did his PhD at Illinois Institute of Technology. He also, about the same time as Keith, started working for SO Production Research before becoming a professor at the University of Oklahoma in 1966. And he did a long stint there, almost 30 years, I think, at the university. He also taught industry courses through the Campbell and Associates organization. And then he started his own consultancy basically after he retired from the university and did a lot of work within the gas transportation part of the midstream industry. We know Ken mainly from his work on developing equation of state models. The first that he really worked on and brought into the petroleum industry was the BWR equation of state, which a lot of people were using and based on a lot of the specific developments that he came up with, which are included in this book that's in the upper right. He also worked with Carnahan and the Carnahan-Starling hard spheres equation of state. He was instrumental in developing the American Gas Association AGA-8 ultra-accurate equation of state for natural gases, both in transportation and metering. And then he was the advisor and co-author of a paper on the most general cubic equation of state by Hamath Kumar. He actually published a paper in the 60s on developing, doing EOS model tuning with the BWR equation of state for petroleum systems. And then some of the last work he did was on pipeline gas dew point calculations based on I think it's called cold mirror method of measuring dew point for natural gases, and showed how the description of very small amounts of the C7 plus in the gas had a profound effect on the ability to predict accurately and tune the equation of state to these measurements of dew point. So let's see, we've got this first paper in 1966 in the SPE journal about an approach for determining equation state parameters, BWR parameters, using phase equilibrium data. So he was first out on that. In that paper, interestingly, he uses an equation to basically smooth high pressure K-value data that are used in the tuning of the equation of state. That's essentially identical with the Hoffman KPF equilibrium QC plot. Basically the same equation, where this log Ki star is just the K values of a mixture at 1 atmosphere and the temperature of interest, whereas the K values here on the left are the K values of a mixture at pressure and temperature. So it's the same equation, and he makes use of that for QCing and smoothing K value data to use in the tuning. The Carnahan-Starling equation of state is not as much used in the industry, to my knowledge. Came out in 1969 and was particularly accurate for certain systems. This is the cover page of the PhD thesis of Hemant Kumar on the most general cubic equation of state, shown here on the lower right in 1980. Then the 1992 AGA equation of state for natural gases, shown here. Now I think it's been superseded by the Gerg equation of state developed in Europe for similar types of calculations in natural gas systems. Anyway, that's kind of a collection of those contributions that he made on developing equations of state. And then this was his last, I think, paper talking about this prediction of dew points for pipeline gases. The next I wanted to mention was the contributions by Michael Michelson. Michelson, he got his master's degree in 61 to 66. He did not receive a PhD degree, nor did his co-author of the book from 2007, Jürgen Mollerup, who was also a professor at the Danish Technical University in Lyngby, where he and Jürgen were basically, I think, office neighbors, and started essentially at the same time at the university and started their professor positions at the same time, neither one having a PhD, interestingly enough. Michael's first major contribution was in co-authoring a book on collocation methods, which is the solution of differential equation models by polynomial approximation, with Professor Wilhelmsen. But really, we know him mostly from his contributions that started in the late 80s, late 70s, early 80s on computational thermodynamics. He basically looked at computational methods for phase equilibrium calculations and chemical reactions, a wide range of equations of state models. His papers were known for their mathematical rigor. They were innovative. They were often very terse and compact in presentation. Those who had access to his code also found the code being quite compact, and in particular, he was known to be interested in solving these compositional problems with a very fast, efficient algorithm. He pretty much did calculations and published papers on using all the different types of equations of state, but mainly the cubic equation of state. And I kind of classified the 2 years of, or 20 years, 2 decades of Michelson's contributions, talking about the stability analysis, isothermal flash, PT envelopes, critical points, saturation pressures, something that was referred to as the simplified flash calculation, multi-phase flash, isothermal, isenthalpic, isentropic, tricritical point with Bob Heinemann up in Canada, negative flash, an idea of Aaron Zick that we worked together on, and he basically laid out the foundation of what that negative flash calculation was doing. It was not a minimization. It's not really a thermodynamic solution, but it's a solution of the Gibbs energy. It's a saddle point instead of a minimum. He worked on mixing rules for more complex systems where the conventional mixing rules were not valid. Published some important papers on the excess Gibbs energy models, and had a couple of papers just talking about what he considered to be what was easy and what was really difficult in doing these types of calculations. From 2020 until his passing in from 2000 until 2020, he was a co-author on almost 100 different papers. That first 2 decades, he was the primary author of most of the papers, if not the only author. So, like I mentioned, Michael and Jürgen Mollerup published a book, second edition, came in 2017, I believe, on the fundamental computational aspects of thermodynamic models. So that's definitely a go-to book. Can be ordered online from the publisher Tie Line Publications, which I think is Aralyn Stainby is publishing house. Now, I wanted to mention the first two papers that I was reading and studying and making use of, as most of the people in the petroleum industry. It was the isothermal flash problem. And the first part of this two-part paper was on the stability analysis, and the second part was on the flash calculation, the phase split calculation itself. And he tied these two methods and solutions tightly together in pretty much all the work he did, where he generally did a stability analysis, a stability calculation prior to solving the flash calculation, using the results from the stability test. And just to make that kind of a short summary of what did the stability test, basically have a composition and a pressure and temperature. And the stability test tells you that that mixture composition definitively will split into two or more phases if it finds an unstable condition. So when it's doing the stability test, if it finds an unstable condition, what we call an unstable condition, then it's guaranteed that that mixture will split into at least two phases. And if that's the situation, if that's the result of that calculation, then it will give you very good initial estimates of the K values for the equilibrium compositions that you start with in solving the actual flash calculation for two phases. And then if you solve the two-phase calculation, you can do a new stability test on the two-phase equilibrium calculation to identify the possibility that a third phase may be appearing. And you would then go into a new sequence of solving for the third phase and so forth. So basically he stacks this stability flash, top of each other. And I thought I'd just kind of go through and graphically, this is for a two-component system. This is the Gibbs energy on the y-axis and composition on the x-axis. And the surface of the Gibbs energy, basically what you do is you go to the total composition Z and you find the tangent line to that Gibbs energy surface. Okay, so you see the yellow line here, it gives you the tangent. Then you go off looking for lighter fluids to the right or heavier fluids to the left, and actually he recommends you doing both. And what you're looking for is any composition to the right, a lighter composition, or any composition to the left that has a tangent, a slope at its tangent that is the same slope as the tangent at the feed composition Z. So you see here at this YSP, the second phase composition, you find it and you find that the Gibbs energy has exactly the same slope. Now, if that line with the same slope lies below, meaning that the energy at the composition Z is lower than the energy at Z from the tangent itself, that means that this Z is unstable. And if you do a flash calculation, you'll find the mixture Z will split into two phases. Now, what will the two phases look like? Well, the two-phase flash calculation is simply finding the tangent to the surface here, going that tangents both at this point. So I just got to draw it here in a dashed line. So the tangent to the entire surface, that lowest tangent there, gives you the green composition and the red composition. And those are the final equilibrium compositions, Z being between them. So this would be basically this composition is, the Z is very close to the equilibrium oil composition. But that composition that it found when it did the stability analysis, basically having the same slope, gave us a very good estimate of what that second composition would be. So basically the stability test gives you a very good set of K values to start the flash calculation with. And of course, this is for a two-component system, and you can look at this graphically, as did Gibbs when he came up with the concept. But when you have 10 components or 50 components, obviously you can't do a graphical representation of this. And instead, he came up with an algorithm for doing the stability test in a very um, uh, methodic way, and that generally would always find either a solution that said, well, the current feed composition appears to be stable. We can't find any composition that is moving this mixture into a two-phase system. And so that was really this was probably the most important contribution in coming up with that algorithm for the stability test. And that was implemented and used in quite a few of the reservoir simulators and other simulators using an equation of state. Prior to that, you didn't really have this recipe for doing the stability analysis developed by Gibbs. So on the topics, equation of state development, phase equilibrium algorithms, US model tuning, and the equilibrium transport coupling. Let's start with the development equations of state. So back in 1873, van der Waals introduced the first cubic equation of state. And there were later cubic equations of state that we're more familiar with. For example, the Redlich-Kwong came in 1949. And that was basically the advent of computers within the industry and research or the university organizations. Computers became available around 1949. So the Redlich-Kwong equation of state was collected a lot of interest. It was much simpler than, for example, the BWR equation, the Benedict-Webb-Reuven equation of state that came in 1940, which was much more complicated. In 72, Suave developed further the Redlich-Kwong equation of state, making it very accurate for phase equilibrium calculations because it guaranteed that the vapor pressure of any compound at essentially any temperature less than its critical temperature, the vapor pressure would be accurately predicted. And with that accurate vapor pressure prediction from that equation of state, you would be able to get K values at lower pressures like processing conditions. That would be accurate. And then Pang and Robinson, 76, 77 developed a similar, in terms of accuracy and simplicity, cubic equation of state. That basically the SRK and the Pang-Robinson is what the vast majority of people are using today. So let's just start with the van der Waals here in red, the red box. We've got constants A and B. We've got the Redlich-Kwong in the blue box here. Again, two constants A and B. Slightly more complicated. This right term is the attractive forces. The left term is the repulsive forces. The purple box is containing the SRK, which is identical to the Redlich-Kwong, except instead of the square root of square root of temperature term, there's an alpha correction term that's basically a function of temperature and the eccentric factor of the component. And knowing that information, the eccentric factor you can get from the alpha, the value of the correction term needed to get the accurate vapor pressure for that component at that temperature. Then we see basically in the green box, the Pang-Robinson equation of state, slightly more complicated on the attractive term, basically a little bit better volumetric description of liquids between C5 and C10 than the Redlich-Kwong, which was more accurate for liquid densities in the methane and ethane, the lighter components. So basically they all have two constants, A and B. They can be used for pure compounds, and the A and B are calculated for the pure compounds knowing the critical temperature and pressure. And then to get the alpha correction term, to get vapor pressures, you need the component eccentric factor. Then when you're going to use the cubic equation for mixtures, you have simple mixing rules. For the B is the linear mixing rule, and for the A quadratic mixing rule. And this AIJ term is basically using the AI and the AJ terms calculated from this equation here. but you can also include a correction term to the A, which is called the binary interaction parameter, KIJ, which we'll talk about a little bit more later. So these are all of the cubic equations of state that are basically being used today. If we look at the BWR equation of state, this is the one that was introduced and developed by Starling for petroleum systems. It's got 5 constants. You've got a little bit different mixing rules. You've got 4 of the constants using different binary interaction parameters. And this was the equation of state that came in the 1968 paper by Starling, intended to be used for reservoir and production petroleum systems. All of these equations of state basically are giving a relationship, some kind of algebraic equation for pressure as a function of volume, temperature, and the moles of the various components in the mixture. Now, in order to develop an equation of state, you have to come up with a way to find what are the constants in the case of cubic, A and B. And that's usually tied to the critical properties of the component through the van der Waals critical criteria. First and second derivative pressure with respect to volume being 0. And then we also, like in the Suave and the Peng-Robinson, we use the vapor pressure condition to come up with that correction term to the A to give us the accurate vapor pressure description at temperatures below the critical. On the mixing rules, basically for the cubic, we use the linear for the most part to calculate the B, mixture B constant, and a quadratic mixing rule for the A term. Those are the classical mixing rules. Now, if you have more complicated mixture systems, and that would, for example, be if you've got water and hydrocarbons together and you want to do a 3-phase flash calculation or a water hydrocarbon flash 2-phase, then you would need something like the Urán-Vidal mixing rules, which was used and also developed further by, I think, both Michelson and Mohlert independently. Improvements to the Urán-Vidal type of mixing rule that would handle more non-ideal types of mixtures. And the binary interaction parameters come in, obviously, into those mixing rules, as we saw earlier. For the cubic equations, both SRK and Peng-Robinson, the accuracy of calculating petroleum mixture liquid densities with the constant A and B is only around plus minus 5 to 15, 20% accurate. It's not really accurate enough for important engineering calculations where gravity has a major role. Okay, so in the early 80s, there was a group of 3 French authors who published a paper, Penelue volume shift, which introduces a third constant, C, that can readily be determined for each component. And so you basically have 3 constants instead of 2 for each component in the mixture. And using that volume shifted Peng-Robinson or the volume shifted SRK equation of state, you can pretty much, for any petroleum mixture at reservoir conditions, near critical oil surface conditions, get densities within about 1 to 3% accuracy. That volume shift factor may need to be temperature dependent to get that kind of, you can then usually get 1 to 2% accuracy both at surface and reservoir conditions. So basically that's the development of equations of state. There are others around, but I'm not going to go into those. But the cubic equation has really been the workhorse, and rightly so. It's been a very accurate, reliable model for pretty much all of the types of calculations we make in petroleum fluid systems. Now, if it comes to the algorithms, the equilibrium algorithms, phase equilibrium algorithms, we've got the isothermal flash calculation, stability test introduced by Michelson, as a precursor to the flash calculation. It may also be used in connection with calculating saturation pressure, lower and upper saturation pressures, and the critical point. So this diagram is for a constant composition, plots pressure versus temperature. Within the envelope of the green and red line, you basically see the region where we have a so-called positive flash. That means that we have two phases. Each phase amount is greater than zero, physical phase split. Along the green line, of course, we have the bubble point, which means that the second phase appearing is infinitesimally small, but it does appear. So there are two equilibrium phases along the green line, the actual total composition, and then some incipient phase that's appearing as you go from pressures higher past the green line and into the two-phase region. You basically enter the two-phase region. The red line is a dew point. You've got the upper dew point and then the lower dew points. There, the total mixture is a gas phase, where there's an incipient phase, liquid, appearing along that path of pressure and temperature here. The critical point joins that bubble point and dew point together, shown here. There, the calculations are more complicated. The so-called K values approach 1 for all components, but in a very nonlinear manner. So the calculations, the isothermal flash calculation, just around the critical point, they're usually slower, they're more complicated to get a guaranteed convergence, and more difficult. The gray dashed line is what we call the convergence pressure envelope. And basically, between the green or red line and the gray dashed line, you can take that composition. The fluid composition is actually single phase. It's thermodynamically stable. So it will not split into two phases physically. But when you do the calculations with an equation of state, you can find in this region between the green and the gray dashed line and the red and the gray dashed line, you can actually find two equilibrium compositions that are tied to the total composition through the lever rule along the tie line. So the total composition is on the tie line of the equilibrium gas and liquid compositions that are computed. Now, the amount of the one phase will be negative and the amount of the other phase will be greater than 1. But the compositions it finds will, in fact, be thermodynamically in equilibrium. And as you approach this gray dashed line, those two compositions it's finding will approach each other and will actually represent a critical composition at that particular pressure and temperature. So where I'm pointing here, if you look at the calculation, you'll see, oh, the convergence pressure at 200 Fahrenheit is 5,200 psi. And the composition it finds for the two phases that are now approaching each other, that composition will actually not be the same composition as we started with. But if you take that created composition at that pressure and temperature and look at its phase diagram, it will have a critical point at this point. Beyond the gray dashed line, physically it's still single phase, but there will be no two-phase flash calculation result other than the phase is stable. So these are just this kind of a summary of all the main types of calculations that one has if you're just looking at a two-phase system. Now, when we come to the EOS model tuning, we basically can change two things with the equation of state model. You've got the individual component properties, TCPC, acentric factor is needed for each component. But those three numbers are known, let's say, if not exactly, very well for the pure compounds, methane, ethane, propane, maybe down to normal C5. And then you've got the non-hydrocarbons, you know their critical pressures and temperatures of the acentric factor. So there are some compounds that are well-defined, well-known, well-quantified in terms of amount, and we are not going to change those properties in general, okay? But as you get the heavier components, you have many isomers making up a single carbon number C7. And there might be 6, 7, 8 isomers that make up what we call the single carbon number C7. As you go to higher carbon numbers, the amount of possible isomers making up that C10, C15, and so forth just grows, I guess, exponentially. I'm not sure. But so you basically can have many different compounds making up a given single carbon number mixture. They're actually mixtures. And we don't know the makeup of the C10 or the C15 or the C20 exactly. So we have kind of a bracketing value for what the TC/PCA century factor should probably be, but we know it could vary between some lower and upper estimate. So the heavier the component, the more uncertain we basically don't know the TC/PCA centric factor numbers. Even the molecular weights are difficult. So basically we can change some of the properties of the heavier components. And then we've got these binary interaction parameters, which will help us to, let's say, correct the simplicity of the cubic equation of state in describing very complex interaction amongst binaries and other components, and try to better bring in line the model with measured K values, okay, that are giving you the actual signature of that particular mixture, the K values, their approach to the dew point or bubble point, and so forth. So the binary interaction parameters are particularly important for modifying how the K values vary with pressure and temperature. So those are the things we can change, and often we'll change preferably as little as possible to get a match to measured vapor, liquid, and volumetric properties of the mixtures of interest. In addition to that, when we take samples, oil and gas samples, and make those PVT measurements, the compositions of those samples that we take to the laboratory have uncertainty, as well as do the PVT measurements themselves. And those compositional adjustments that we allow ourselves to make are based on the known experimental uncertainties in the laboratory: gas chromatography, the so-called flash of separator oil or reservoir fluids to atmospheric pressure, the flash gas and oil compositions having some uncertainty in their measurement, the recombination of those flash gas and oils to get back to the original composition. So there are composition uncertainties that we try to take into account as well in doing model building for a given fluid system. When it comes to the heavy ends, we basically have the amounts of the different components. We measure those to some extent. There are masses being measured, but we don't measure the properties of the single carbon numbers that are reported in terms of mass. We measure maybe the flashed oil molecular weight. So we have that. We can back out of that the C7 plus molecular weight, which, if you assume an exponential model, will give you basically the distribution you compare with the GC data, or you can tune the gamma model, which is a more flexible molar distribution model, to the gas chromatography data for multiple samples in a field, and see if you can come up with the shape factor, which typically lies between 0.5 and 2 for reservoir fluids, and come up with a common shape factor for all of the fluids in a given fluid system. And each fluid may have a different average molecular weight, but usually they should have the same shape. The gamma model also has the advantage that it gives you molecular weights associated with the mass amount that you've measured. And the biggest uncertainty is in the amount of the heaviest, usually C30 plus or C36 plus in today's laboratory reports. And the amount of the heaviest fraction is the biggest uncertainty, and may need or allow for some adjustment. And they can have a considerable effect on the prediction of, for example, dew points for gas condensates, minimum miscibility pressure. So the amount and the heaviness of the C, let's say 36 plus, can be important in EOS modeling. The properties being assigned to all those individual fractions in your EUS model after the heavier components are uncertain, they become more uncertain the heavier the molecular weight. There are different correlations that you can use. Typically, we try to use crude distillation data to come up with single carbon number models for the molecular weight, specific gravity, and normal boiling point. These are properties that can be measured in a distillation analysis. We try to apply those to the mixtures and coming up with EUS model, and honor those together with correlations that are published, different correlations, to get our initial estimate of these properties. And then we allow a slight adjustment of those. The heavier the component, the more adjustment we allow, typically up to maximum of about 5% change from what the correlations are giving us as our initial estimate. On the binary interaction parameters, basically they're going to have the biggest impact on the K values of the individual components, particularly the components I and J, if you have them. They'll affect significantly the saturation pressure and the amount of each phase if it goes into the two-phase region. The original binary interaction parameters were proposed and correlations were given by Prausnitz and coworker Chu in 1968. The Chu-Prausnitz correlation is often used as a starting point to assign binary interaction parameters for hydrocarbon pairs. Now, as I mentioned earlier, the binaries in the cubic equation will only be affecting the A term. Now, if you don't have any binary interaction parameters in a mixture, then you basically get this quadratic mixing rule for A. And Michelson and paper in the mid-80s basically showed that you could solve directly that if you have 0 bips, then the K value from the cubic equation state will always follow exactly this relationship. AI and BI are just the equation state constants for that particular component. Log Ki is this simple relationship where the 3 constants will vary with pressure and temperature, but it'll exactly follow that relationship. Now, we almost always have to have non-zero bips, and if we have non-zero bips, which we always have to have for the non-hydrocarbons, nitrogen, CO2, H2S, and they generally are positive and in the range of 0.05 to 0.15, these non-zero binary interaction parameters will have most effect on the K values, the equilibrium K ratios of components I and J. But in fact, well, if you've got 10 components mixture and you have only a single binary interaction parameter, it will in fact change the K value pressure behavior for all components. The closer you get to the saturation pressure or a critical point, the more impact those binary interaction parameters will have on the phase behavior and the equilibrium K ratios. This is the equation for A. This is how this is introduced to the mixing rule. So if you're calculating for an oil phase, you'd be using the XI compositions. If you're calculating A for the vapor phase, you'd be using the gas compositions. Or if you're looking at using the equation state for the total mixture composition, you would be using ZI for the total composition here to calculate the average A. There's a very complex and not very well-defined cause and effect relationship between the K values and the binary interaction parameters. This is something I think that just the more work, the more people can do and looking at that relationship and trying to better understand that relationship, the better off we will be in our ability to fine-tune the equation state to measure laboratory data. On sample composition adjustments, we basically have 4 sources of lab uncertainties. We have the recombination GOR, which would be either for separator samples, where the recombination GOR that is used in the laboratory could be slightly different or somewhat different, maybe as much as 5% different than what was reported from the laboratory, from the field, and the laboratory was supposed to use to do the physical recombination. So there's just some uncertainty in how much gas and oil they recombine back together. Composition of the separator compositions could also be an error. It could be leakage on the way to the laboratory and various other sources of potential separator composition errors. Then you've got the chromatographic analysis, the molecular weight of the C7 plus, for example. Chromatographic analysis could lead to errors in the amounts of the single carbon numbers from C7 up to let's say 36 plus. And you basically need to be able to identify whether or not such errors or uncertainties exist, and if so, how to correct them. So our approach to doing that is to have a field-wide gamma model that's fit to all samples with extended analysis. And then those samples that are outliers, that where the model is fitting the vast majority of samples accurately. If you have some samples where that same model is not fitting those data, then we will either not use the data or we will try to correct the compositional data with the field-wide gamma model. The most uncertain amount is the heaviest component, and that's for various reasons. The GC analysis method requires use of internal standards because it doesn't basically integrate or quantify that amount of the heaviest. It back calculates it, which can be an uncertain back calculation result. So the last topic that I want to mention is just examples of where equilibrium calculations and transport calculations are being coupled together. And of course, reservoir simulation is obviously one of those. But another one that's a little bit of interest is that of an interfacial boundary where you've got basically a non-equilibrium vapor in contact with a non-equilibrium liquid, and this could be at a pore level, it could be at a naturally fractured reservoir. You could have the gas in the fractures being a different gas composition than what's in the matrix block. And so basically you've got a transport and you've got boundaries. So you've got transport across the boundary, you've got phase equilibrium at the boundary, and you've got material balance. So basically this is a solution to a problem where you fill a PVT cell with, for example, a stock tank oil. And then you charge it with nitrogen, as we did in the experiments back in the 1980s. We were interested in the diffusion coefficients of nitrogen in crude oils. So we basically took a stock tank oil, we charged it with nitrogen up to 300-400 bar, and then we observed the pressure change with time and the interface level change with time. And then that change with time of the pressure in particular, and also the liquid level, were mainly controlled by the diffusion coefficient of nitrogen in that oil. So then we back calculated the nitrogen diffusion coefficient from those experiments. So it's an interesting, and Mikkelsen took and basically combined his knowledge of the collocation methods to take this solution of diffusion in a moving boundary problem, diffusion in the liquid phase, diffusion in the vapor phase, with the boundary conditions that were required at the interface. It was an interesting problem. And then another is that of multi-contact developed miscibility. And Aaron Zick in 1986 described what was prior to that unknown so-called mixed condensing vaporizing miscibility process, wherein a injection, here we've got a one-dimensional flow like a slim tube. We inject on the left, we produce on the right. After about a half a pore volume injected, you develop a near critical miscible-like front. And behind that front, you basically have recovered all of the oil. And at the front, the K values here being plotted versus distance approach 1 at the front. And you can develop this near miscible front, which upstream of the front, you have a severe kind of vaporization going on. So you get components being moved from the oil into the gas. And just beyond the front, in upstream to the front is a condensing where those same components are being dropped back into the oil ahead of the front. And then that front just propagates through the reservoir, and you basically recover all of the oil behind the front. So these are two examples where you're coupling the equilibrium calculations with some form of transport mixing. So that's pretty much it. And I'll try to field any questions about what I've gone through.
Yeah, 100%. Great, Curtis. See, we got a lot of questions in the chat here. You touched a little bit upon it, kind of the work you've done since the 80s on kind of field-wide EOS modeling. I see some of the questions are kind of related to some specific examples of that, where we've done it, how it kind of started in the first place. Can you give a couple of cents on kind of these field-wide EOS models and how that has kind of changed from the 1980s, I guess, until today, and where we've done it?
Yeah, so we really started doing this in the in the mid 80s, early 80s. We were in the Ecofisk area, and basically, you've got the a lot of reservoirs have wide ranges of composition. I mean, Tom Schulte's paper in 1980, the Berber field in Oman, and Brent field in the UK, and many fields in the North Sea. In one reservoir where there's all this fluid communication going on, from in situ fluids to fluids as they're being produced, you need to describe all this wide variety of fluids, gas cap, oil, compositional gradient, gas cap into oil through a critical undersaturated transition. The equation of state has to be able to describe all of those in situ fluids initially and as they develop over time. So you can't just take one sample, fit the equation of state to one sample, and just expect it to extrapolate and predict the PVT properties of all the other samples at the same time. So we basically were doing this at a very early stage for most of the fields that we were developing equations of state for. We would try to take as many samples as we could get a hold of, and they could be gas cap, oil, different types of GOR oil. So, and use all the samples, all of their PVT data, but a single equation of state. So we've been doing it since the mid 80s, the early 80s. We've done it for, I would think hundreds of fields around the world. So now, 10 years ago, we started on the tight unconventionals, the liquid-rich tight unconventional fields in the US and Canada. So we've developed basin-wide equations of state for Permian, for Eagle Ford, for Bakken, for, I think, Powder River, we're just finishing now, Montney and Duvernay in Canada, some of the big fields in Argentina and in Saudi Arabia, one of the tight unconventional fields there. So we've done, in the tight unconventional, it's more on a basin-wide than it is on field-wide, so to speak. So it's something that we've done a lot of, and always try to make an effort to do it. On occasion, you have to have multiple equations of state for a given, let's say, field. But generally speaking, we are successful in building single equation of state that handles a multitude of different layers, zones, and regions of a given field.
Great. The other question that kind of a common denominator of some of the questions is related to kind of pure components. You see the last few years, like hydrogen, CO2, equations of state that are working very well for those type of systems as well. Are the equations of state that we've been using in the past, like Peng-Robinson SRK, with just a few tweaks, good enough to model those systems, or do we have to do something special with especially, I guess, nitrogen, CO2, or methane, like pure single component systems?
Yeah, so I think we've just recently done work on hydrogen, which looks very promising using cubic equation of state. So that is actually quite promising on both volumetric and transport viscosity. We actually present a paper on that at the upcoming EAGE SPE conference this summer, I think, giving both data and EUS modeling. And we're also comparing with some of the kind of ultra accurate, the NIST, the NIST models as well, GERG models, comparing. And the Peng Robinson actually is doing a very good job for those systems that we looked at. Water, H2O, has been shown you can actually model with the cubic equation of state water and non-aqueous phases, gas and oil, very accurately on the component partitioning, mutual solubilities. In a few different ways, you can do that quite accurately, very accurately, I'd say, for the most part. What hasn't really been done properly for the water, I would say, is to get the compressibility of the water accurate. You can get solubilities, but the water compressibility predicted by the cubic equation of state is just, it's off anywhere from 20 to 40, 50%. So something needs to be done there. We working some things, but that's not really been solved yet. CO2, I think, for a given application in general, a cubic does a good job, can do a very good job. The 3-parameter cubic equation of state. And I'm sure you're always going to find exceptions, and it depends a little bit how wide the range of pressure, temperature, composition, space you're looking at trying to model with a given model, with a given equation of state. So for a given application. But yeah, in general, the cubic looks very promising for a lot of what's going on with the hydrogen, CO2, natural gas systems. I'm pretty optimistic.
Christoph, we're running a little bit over time, so we'll end with that question there, Curtis. If you all have any questions that you'd like to ask us, feel free to reach out to any of the emails that's on the screen. Curtis has all of them on the slide deck there. The recording will be distributed later today, and we'd like to thank everyone for joining our webinar, and you have a good rest of the day. Thanks, Curtis.
Thanks, everybody.